this is a process of submitting a job electronically. So to submit the E-beam job, you go to E-beam left tab, then make VB6 booking. Then you do the job name, which is your initials, followed by the job name, then the sample ID, which is 23792. The thickness of the sample, this is very important. You need to measure this using the micrometer in the aqueous processing room. Then, because this is a registration job, the cross position, which I'll make up at the moment, because I can actually measure that. You need to attach an image file of what the sample actually looks like, so the E-beam operator can load it the right way around. So you want to choose file. Then you need to find where I've saved it, which is in a convoluted space. VB6 submission design. So we attach the file, and then we have to give notes. So because this is a registration job, I'm going to use please use circle cross. And you have to type in your phone number in case there's any problems. Then you press submit. So then it comes up everything that you've entered. Comes up with the image that you expect for the operator to actually align correctly for the registration job, and then you just press submit, and it says the job loaded in it. And if we go to view VB6 bookings, you can see that it appears here. And it's going to take 0.168 hours.
Okay, so this is the box where users put their samples when they submit a job to the VB6. And what the operator does is come here, find a sample, and load it in first of all. So I'll take this sample here, which you might like to look at closely, and we'll take it through into the control room. Now the first thing to do is to link this sample with one of the jobs which a user has submitted, which is on this screen here. That's not always very easy. It depends how neatly this has been written. But I can just about make out James G at the top, James Grant. And if we look here, we can find that James Grant has submitted a sample. It's JG614. And if you look here, it has a, well, maybe you can read 614. The sample is easier to read, 23792. 23792. So you have a positive identification, that's the correct sample, and we can go ahead and load it. One of the big problems we have is that samples are often here, but they're not in the box outside, or they're in the box outside, but they're not here. We can only load a job if it's in both places at once. And you'll notice that there are about 8 jobs here, but there are only 2 samples outside. This is a constant frustration for the operators. But they come here and the jobs are not ready to be loaded. Okay, let's go in. So this is the class 10 clean area. You need to wear face mask and gloves while you're in here. First thing to do is to unload the holders from the VB6. This is the load unload area. And if we come around here, we can see how to do the unloading. There's an airlock pump, airlock vent, and so by pressing these buttons we can take samples out. What we'll notice is on this rack here we store many of the holders during the day when we're loading and unloading, rather than having to take them out of the cassette on the VB. And so there's lots of cassettes already available here, so we'll put this sample in one of these cassettes. So the first stage in the process is to work out which holder to place the sample into. And to do that, I need to look closely at the job submission form and see what the sample thickness is and any special requirements. Okay, so the first job is to look closely at the job details here and make sure that when we load it, that we do so correctly and in accordance with the user instructions. So here's the job in question, this one at the bottom, and I can click on the L icon here for load. Oops, I click correctly, and it gives me, for instance, the thickness is 800 microns. Now 800 microns is an unusual thickness. Most wafers are thinner than that. So this of course means that we have to have a special holder dedicated to this sample. The other thing we can see here is registration yes, and that tells me that the sample needs to be aligned and that we need to be very careful as we load it up to get the alignment correct. Here is the user image, and it tells me that there's a scratch in the bottom left corner, which then means that I know which way round to put the sample when I load it onto the holder. And if I look further down, I can see any user instructions, and he simply says use the circled cross. So let's see if I can find the circled cross. Do the instructions work? Yes. Up here we can see a cross that's been circled, so that's the one we should be using. So next job is to get the correct holder. So we can come across here. Now remember, this is an 800 micron thick small piece, so I'm going to use this particular holder here. This is set up to take small pieces. And all it is a 4-inch plate with clamps on it, so we can clamp the sample, and height references which we can change the thickness of. If you look carefully, that one says 375, which means it's the wrong thickness for the sample we have in hand, but so one of the first jobs will be to change the thickness of the height references. Height references are kept in a drawer. I'll go and fetch some. So here we can see we keep height references of different thicknesses. I need the 375 one to put the old ones away first of all, and then we'll put the new ones in second. So this one, as you can see, is labelled 0.8. So I believe it should be 800 micron thick pieces. And if you look carefully at them, they're all labelled 800. So somebody in the past has carefully moved the tweezers so you can see the 800. So somebody in the past has carefully measured all these thicknesses, so I don't need to double check at this point. I can just assume these are all, as labelled, 800 microns. You need to carefully put them under the height sapphires here. There's springs under the plate which push it up, and it's held in 3 positions which will keep it nice and planar. It's important that I check that these are not going to fall out, so I give them a little sideways push. If they did fall out and land somewhere in the machine, it could cause damage, so clearly it's important to double check there. Next stage is to load the sample. Now if we look again carefully at the box, we can see that James has written a U in a circle just here. And what that means is the sample is up the right way. And if I open the box, you can see very clearly that it's the right way up, and also that there's a cross very clearly marked, so I know which orientation to put it. The cross goes at the bottom left corner. Okay, the next stage then is to load it in here, but of course I need to be very careful to put the cross at the bottom left corner. Now you might think that this is the bottom left corner. You'd be wrong. It's a slightly complicated situation. If we look at the wall, we can see the axis orientation, and we can see that the bottom left is actually at the top left as you look at it, but only as you look at it with the Faraday cup in that position, which means I would have to turn this to 180 degrees and then the top left corner would be here. Now, the reason for having that diagram there is because this is the orientation it comes into the alignment microscope later. So if I leave it here at that orientation, so I don't change it, I now know that my cross goes at the top left corner. And this is a very important part of loading, that we get it around the right way. Because it's nicely put together, I know I can hold it around the edges without causing any damage for a sample like this. So I simply need to put it somewhere. This clamp is going to be suitable, and I need to clamp it up. Users often ask for the minimum amount of clamping on their samples. What you have to be aware of is if you don't put enough of the sample under the clamp, the sample won't sit flat. So there I've got about 1 millimetre of the sample under the clamp. And if I tighten that, the sample, instead of sitting flat, will actually tilt up like that. And that's no good. I need to put a little bit more under the clamp to make sure it's going to sit flat. And then clamp it there. What I usually do is I then just push the sample here, and if it moves at all, you can usually see it quite clearly. In fact, I can see that's moving. But I think it's not moving too much. Judgment call. What I'd now do is I put it into the alignment microscope, and there I can actually measure the flatness and I can measure the rotation. put on the laser. Put on the light. So we need to measure the height of the sample using the laser. You can see how the laser system works. There's a laser beam comes in here, bounces off the sample, roughly where that focus of light is. That light's not the laser, it comes from the microscope, and the detector is here. The reading from the laser is over here, so at the moment it's reading 80 microns. Ideally, it should be within plus or minus 50 microns. So what we're saying is this sample is too high, so I need to adjust the height. And that means adjusting these height references in the corners. But before I do that, I want to check not just that it's, okay, I want to check that it's simply a matter of height and not a matter of tilt. And I can do that by starting that there. I'm now going to move the stage by 1 millimeter in X. You can watch it move a millimeter in X here. Yeah, and it's moved by 7 microns. There's a huge tilt as well. So there's a tilt of 7 microns a millimeter in X. You can see, if you watch the height meter, as I move slowly in X, it's not so bad. Okay, it's 73 millimeters in X. .78 millimeters in X, so it's 5 millimeters in X, and it's changed by 40 microns. That's about 8 microns a millimeter. That's not good. So there's two problems here. One is that the sample is tilted, and the other one is that the sample is too high. Final check, let's have a look in the Y direction. So I'm going to put it more into the middle of the sample and then do the Y direction. And the tilt in the Y direction is much, much less. If you notice that. It is moving, but not so much. So there's two issues, and it needs to come out and be readjusted. Now, if you remember what I said earlier, I was pushing it here and said I could detect a small amount of motion. And actually, all the error is in that direction, which suggests it might be the clamping here that's causing the problem. There's two ways around that. One is to clamp more securely by increasing the amount of sample under the clamp. And the second one is to put a second clamp up here to hold it down at this end. Because the bit that's going to be written on is this small chip in the middle here, I've got a millimeter or so extra I can clamp, so that's the first thing I'm going to try. Okay, so I've clamped it more securely. We'll see whether that helps in the setting up of the height. So you can see that the operator has a painstaking job here with small samples, that you don't just simply throw them in the machine. They need to be adjusted and readjusted until they're correct. So let's switch the laser back on again and move in the X direction. So it starts off at 90, and goes to about 60 microns. There's still quite a big tilt, and the height is still a bit wrong. So that suggests that an extra clamp would help. It also suggests that we really do need to change the actual height. One thing at a time, so we need to add an extra clamp to this sample. So let's choose a clamp. And the problem is that the clamps only go in certain locations. And on this particular holder, you can see the screws are not central, which means the clamp can only go in two directions. I can't easily put a clamp facing that way. I can make a clamp face that way and then move the sample a little bit towards it, and that should work. Sorry, this is awkward. There we are. So it's now two clamps which are effectively on opposite corners. Okay. Now let's try the height again. I suspect that might have improved the tilt, but it won't help with the height offset. Now it's also, of course, quite possible that on this sample, which is basically a small chip mounted on a bigger chip, it's possible that the tilt is partly caused by the gluing process, and there's nothing we can do about it. So laser spot on the sample, switch the regulator on. Let's move in the X direction and see what happens. It's the Y direction, oops, sorry. So that direction is Y, it's fine. X goes from 96 to about 60. Still roughly the same tilt, nothing I can do. What I'll try and do, therefore, is adjust the overall height of the sample to be correct, but there's really nothing I can do about the tilt, and I'm going to assume that it's caused by the gluing process, but that's difficult to measure because the laser won't work on the underlying silicon piece without adjusting the height pieces. So the height is about 70 to 80 microns long, so I need to look for a slightly thicker set of height pieces. Let's see what we can find. 1 micron, 1.1, 900. Well, 900 would be about right, I think. So let's try those. That's the 0.8s back in their box. Get 3.9s. Here, here, and here, and again check that they're properly clamped in place. And let's go and look at the sample height again. There we are. Put the laser on. Now the height is pleasing. It's minus 22. It's quite slopey in that direction, but we've tried quite hard, and I'm going to assume in fact it's a small piece mounted on another small piece, and there's limited amount we can actually do about that. The next job is to check the sample alignment. Because it's a registration job, the sample has to be mounted with an accuracy of alignment within 0.2 degrees. And to do that, we use this microscope here. I'll look through here first of all to find the alignment marks on the sample. Now, so this is a manual operation, and what the operator has to do is to run the sample across its length, watching the crosshair and seeing how off true the rotation is. And then we can nudge the sample with a pair of tweezers until we get the alignment as close as we can. Now this sample is going to be particularly difficult because it's got two clamps. If you've got a single clamp, it rotates easily about that clamp. If you've got two clamps, it won't rotate at all. So you have to loosen one of them off to do the alignment and then tighten it up afterwards. So I'm going to do that just now. I'm going to loosen up this clamp completely, otherwise I won't be able to rotate it. And then after we've got the rotation correct, I will re-clamp that particular one. Okay, I can see it's quite badly aligned by moving from one end to the other. I need to nudge it in one direction or the other. So, small nudge. Let's see what I've done. That's actually made it worse, so I need to go in the other direction. This is partly because I haven't done this for a while and I've forgotten which way is which. Try that. Okay, it's a lot better than it was. I need to go back the other direction slightly. What I'm noticing is that that clamp's a little bit loose, and the slightest movement, slightest nudge moves it a long way. So I'm going to tighten this clamp just a little bit, and then just go back and recheck. Okay, I want a very slight nudge away from me. Try that. No, that's not quite enough. Better, but not quite there. And that is just about perfect. I can run from one end of the sample to the other without any motion. So as you can see, aligning it to within 0.2 degrees is quite tricky when you've got a small sample and you're just pushing it by hand. But it's something you get used to doing. I'm going to tighten that clamp there, just to hold it correctly now. And finally, I want to check that that action hasn't ruined the alignment. No, that's fine. That's good. So the sample's on the holder. The height's been adjusted as well as I can. The alignment's been done. The last thing before I mount it into the machine is that I need to locate exactly where it is. So when I put it into the VB6 and find it using the electron beam, I know where I'm going. So I'm going to do that by measuring the distance from the Faraday cup to the sample. So the Faraday cup is that hole there, and the idea is that we make sure that the XY position is centered. So it is pretty much centered. The previous operator did it, and within a couple hundred microns is probably as best as you can do by eye. So I then place the spot on the sample and measure this distance, and that is the distance from the Faraday cup to the center of the sample, and that will help us to find it. And I need to add that number to the web page. Because I've been so slow, it's logged me out. I need to log in again. So I need some data. I need to tell it which holder it's in, which is number 388. And I need to give it the position from the Faraday cup, which is minus 74 and 45. I don't bother giving it fractions of a millimetre, because I don't believe I can measure it that accurately. So now we know exactly where it is, and it's ready to go into the VB6. If we come across here, this is the loading area, and as I said before, the vent button's around the corner, and we need to vent the airlock, which I do here. that's now venting. It takes 2 or 3 minutes to vent, and when it's vented it will make a big hissing sound, especially if I have the door open. So that will tell us. In the meanwhile, I can take the sample and the holder out of the alignment microscope and place it on the loading bay, ready to go into the VB6. I can do some tidying up. So I have 2 boxes of sample thicknesses which need to come back here. Oops, here. And back into there. And I have a box which belongs to James Grant and his sample. I need to put this somewhere where we can link it back to the sample later. His sample is in this holder, and as you can see there's a crude eye position of D5. You can see the numbers and the letters, so D5 will find his sample. So I write D5 on the back, holder 388. So when you see writing at the back of your sample, this is what the operator's been doing so that they can know where to unload it the next time. This is especially important if it's a different person the next day who's unloading the sample, which sometimes happens. So we need a system which works. So if we look here, holder 388, position 8, and I simply place that in there, and that's ready for tomorrow. At the moment, we'll notice that the load lock's in position 5, so I'm going to change that to position 8. Now I can open the door. I can open here. If you look inside, maybe if I add some illumination, it helps you to see better. Okay. You can see the slots where it's going to go. And to put it in, I do this, push it in, down and out, and then I need to do a visual check to make sure that it is properly in place. And once you pull the sledge out, you need a visual check that the sample holder is properly loaded. This is what I'm doing at the moment, and I can see that it's in the correct position, and so I close this door. So there's the sample there. This outer door and these 2 green buttons are a safety device to prevent operators from losing their fingers. So to close the inner door, we close the outer door first, which helps the safety. We press the door button, but this doesn't yet close the door. I have to press both this green button here and this green button up here simultaneously, and that then closes the door. And the idea is that if I've got both hands stretched out apart from each other, I won't have my hands inside the door when it closes and cut my fingers off. So now the sample is on its holder, it's loaded into the airlock, and all I need to do is come round here and press airlock pump. It pumps out the airlock. And the airlock will now take about 20 minutes to pump out, after which point we can start to set up the job. Normally speaking, the operator would load 10, 15, 20 jobs before pumping everything down. I've only loaded one sample this time just to show the idea of how the process is done. While we're standing here, I can introduce you to various parts of the VB6. So what you can see here is known as a standalone EHT unit. And what it consists of is a 100 kV supply at the bottom, and in the upper part of the cabinet there is floating electronics sitting at 100 kV which manages and drives the gun. And there are 3 different electrodes floating at 100 kV which have to be controlled precisely to run one part in about 10 to the 5 in order to keep the performance steady. So that's all done here in the so-called hot box. At the top of the hot box you can see the HT cable, the big fat cable, coming out and coming through to the gun on the left here as I'm pointing. And at the top there, just below the cable, is the field emission gun where the electrons start, and they work their way through the column down to the stage area, which is at the same height as the loading bay we saw earlier. So when the holder is loaded, it just comes through a central robot area to the stage, which is here, directly underneath the beam. Other things which you might recognize are pumps. This is 9 getter pump. There's another one at the top. There's 2 which pump out the gun chamber. There's another one here halfway down which keeps the column under a good vacuum. There are 2 turbo pumps which are underneath the system. You can't see them because of the covers. One under here which is the airlock pump, and one under here which is the system pump. If we look here, this panel is known as the mimic panel, and it gives an idea of what the vacuum is doing at any moment. So for instance, we can see the gun, IGP1, IGP2, both lit up. When something is lit up, it means it's on and it's good. If something is flashing, that means it's amiss, something's gone wrong. You can also see, for instance, on the stage there's a light on, which tells me there's a holder on the stage, and it also tells me there's a holder on the airlock. So this light, and in the middle there's the robot, and occasionally we have robot errors, and the robot is the device which transfers holders from the airlock across to the stage. And the robot is situated in this central region here. The light here is this one here, which is labelled PE1, which is the penning on the load lock area. When this lights up, that tells us that the load lock is under vacuum, and we're then able to load our holders onto the stage. So nothing else can happen for the time being until this light lights up. One thing you'll notice about this whole display is it's back to front. It's got the airlock on this side and the column on this side, whereas in reality it's the other way around. The airlock's on this side and the column's over here. The reason for that is that normally this panel sits on the other side, across there, facing in that direction, but the way we've set the VB6 up here at Glasgow means we have it here and everything's round the wrong way. While we're waiting for the vacuum to be good, I can check the vacuum here with the DVAC command, display vacuum, and if I look here, airlock penning is 410 to the minus 6, which is almost good enough. And actually, if I now look at the mimic panel, you can see that that top light has come on. And so everything's ready and we can load the holder. So to load the holder, it's very easy. I just type subload 388. And what that will do is automatically take out the holder that's already on the stage and replace it with holder 388. So the first thing it does at the moment is it waits for a minute doing nothing. And the reason for that is that most of the robot errors happen in that first minute, and we're just letting the system settle. So okay, let's look at various things we have in this room. So this is the monitor and keyboard for the Linux workstation, which runs the whole VB6. Here is just a laptop PC, which is very useful because that means I can have a website running on here, an extra screen effectively. This is the SEM monitor. So the VB6 can act as an SEM, which means that we can find your cross or your markers or the corner of your sample using this. Of course, when we're finding your sample using the SEM monitor, we're exposing the resistor at the same time, so we have to be very careful. And then finally, we have this oscilloscope, which is in XY mode and simply has a spot which tells us the position of the main field deflection. And at the moment, the main field is doing nothing. When it's exposing a pattern, you will see this exposing the shape of your pattern. When it's doing calibrations, you'll see it dancing around doing calibrations. So as a diagnostic tool, it's quite useful. Now if you look here, we can see the system starting to do the unload. It's got another 60-second delay while it's waiting for the robot to settle down and to avoid robot errors at the moment. This shouldn't be normally necessary. One thing I can see here while we're waiting is it tells me that the beam current is 3.99, which says that we have the 4 nanoamp beam loaded, and the 4 nanoamp beam is the one we use for setting up jobs. The reason for that is that it gives a good SEM image with a fairly minimal beam current. If we use the 1 nanoamp, it's sometimes a little bit hard to see. If we use the 64 nanoamp beam, it'll expose your sample very heavily. So we use the 4 nanoamp beam as a compromise. While I'm waiting for the load process to complete, I'm going to log on here and have the website ready for action. So I'm logged on, I come here, I can do view loaded, which lists all the jobs which are loaded into the machine, and you can see that JG614 is the sample just loaded, and that's all sitting there ready for action. So we're now simply waiting for the robot to complete its job, loading the sample before we can do anything else. If I explain this screen a little bit, we have the console here, and this is the so-called opera window, which is where we type all the commands to the VB6. Here we have a basic display of the machine setup, so you can see the EHT is 100 kV, we can see some of the filament settings, its current, and the suppressor is one of the electrodes which controls the emission. The beam current is 3.99 nanoamps, and various other parameters across here. This display is quite useful. It's the gain and back off, which for an SEM effectively means gain is contrast and back off is the background level we can raise or lower. And those are what we'll use to get a good image on the SEM screen. We're still waiting for the substrate transfer to finish. It's finished the unload and now it's loading. So the original holder's been taken out and it's now started to move the holder into this stage area. This will take another few seconds to complete. Right, now we have the opera window ready for action, and I can start various commands. And the first thing I'm going to do is a command which we run once a day, which is AJ new. AJ means add a job. New means I'm wiping all the previous jobs off the batch file. So we've got a new batch file ready to run for today. What I need to do first of all is to run an LJ command, LJ for list jobs, and it says what jobs are loaded, and in particular you can see these two little arrows here, and they tell us which jobs are loaded into the current holder. And this is the job which we just loaded, into holder 388, and what I need to do is to run this command here, M3, which will move the stage roughly to the center of the job. You can see that it moves the Faraday cup, and then by the relative distance, minus 74.45, and those are the same numbers as I typed into the website earlier. So I should now be sitting in the middle of his job. The next thing I need to do is to find the corner of the job without exposing it. And to do that, there's an FC command, find corner, and this uses the height meter, which will measure the height on the sample and gradually move towards the bottom left, recording the height as it goes. When it falls off the sample, it can't measure the height, it sees the height error, and we say we found the bottom left corner. We can see the heights are around about 50 microns, and the slope here is 4 microns per millimeter. It's a little bit high, but we knew it's going to be high for this sample anyway. Ideally, the sample height should be between plus or minus 50. It just raises to a little bit over 50, which is not ideal, but I'm going to accept it for this particular job so we can show you the complete process. And we know the sample is quite tilted anyway, which means the absolute accuracy is going to be compromised. It says we found the corner, so I can now switch on the joystick. Which is here. I can zoom out to the lowest magnification, switch on the SEM, switch it off again. You see we're not quite at the corner. There's the bottom of the sample, and I think that's the left of the sample, so I need to move a little bit. I'm going to do that in a second. The step sizes are set to 1 micron at the moment. I'll just move them to big step size. Go a long way. Now I can zoom in. Very nice clear corner, beautifully cut. Most people's corners are not so precise. So I've now blanked it. So I've now found the bottom left corner of the sample. And I'm going to save that position just in case anything goes wrong. The SP command will save the corner position. And then I can do the MC command, which is move cross. And this is the distance which the user has measured in the Zeiss optical microscope, which should take me exactly to the cross. So if I switch the joystick on now, I should see it. I'm going to zoom out a little bit, switch on the joystick, and you can see straight away I'm at a cross. Just need to center it. I need to zoom in. This is a fairly fat cross, which is not ideal. Thinner arms make it much easier to center. You can see here a little cross drawn at the center of the screen, and that represents the center position. What I need to do is to have the cross centered so its center is there. for a job like this, for cross like this, it's sometimes easier just to look at these 4 corners and try and get those as equal as possible. And that will do. So we've now moved to the centre of the cross as far as we can say. And again, I'm going to save that as the cross position. So if anything goes wrong, I can quickly get back to it. I now need to test the job and make sure that it can find its markers and run correctly. So the command here is simply AJ, which means add job, and it knows it's a registration job, and I say yes, so shall I check it out, and it will run the job but only in test mode, and in test mode it will simply do a very basic calibration, focusing the beam, and then check the heights on the job, make sure it can measure the height, and then look for the markers. And if it can find the markers, then it's happy. So at the moment it's measuring the heights, it's hovering around about 50 microns, which is just about at the limits. It's going to run through a number of basic commands which are displayed on the screen here. And then it will move to the markers and try and find them. And this is where things typically can go wrong. And if it can't find the markers, we then need to adjust the marker search parameters, possibly contacting the user at the same time so that they are aware of the problem. At the moment it's doing the video adjust, and you see it's gone off the screen. You saw a nice top hat image which shows that there's a very clear looking marker. If you look over here, we can see the spot dancing around looking for markers. It's now finished. An experienced eye would say that it's finding the markers quite happily, and if you look here, it's found the 4 markers. It's got expected positions, actual positions, so it's happy. Registration test is successful, and the sample is loaded. What I'm going to do here is just scroll up a little bit, because one thing I can do is check that the rotation is correct. So the rotation really is 0 degrees. You can see the expected positions and the actual positions. The actual positions are slightly different from the expected. So the angle of rotation isn't precisely 0. You can see there's a rotation of 0.001 on the DAC settings, which is not precisely 0, but it's close enough to 0 to be effectively 0 in terms of degrees. What we'll do now, because this is a very short job, is we'll run it during the daytime so you can actually see it exposing real time on the system. So if I were to do cat look at the batch file, there's just a single job in the batch file, which is the job we've got just here. It's a very short job, so we can run it in 10 minutes or so. So to run the jobs, we type run_batch, and this will set up all the jobs. Normally overnight there'll be a lot of jobs, but we're just running one at the moment. Set it going. Here we have some basic setups which we do for all jobs before we set it going. Now it lists it, and it gives us a 10 seconds before starting. This is for the operator, that if they have any last minute panics, they can stop with Control-C before anything happens. And now it's started. It says running this job. You won't see very much on this particular screen. All the information is being sent to a log file. What you can see over here is occasionally the little dot dancing around when something happens. And we'll look at that in a few minutes when it starts calibrating. I'll point things out. So this job will take about 10 minutes to run, then it will finish and we can unload it and return it to the user. Most jobs get written overnight in a batch queue which runs starting from about 5 o'clock through till about 9 o'clock the following morning. So you can't really see much here, but it's calibrating at the moment. If you look very carefully, you can just see the spot moving slightly. Some of the calibrations are more obvious than others. At the moment it's doing the STIG calibration, which doesn't need much of a beam movement. In due course it's going to do various other calibrations, and then it will start to find markers and run the job. Okay, I'll have a pause there. So it's doing some further calibrations now. You can see perhaps it looks a little bit more exciting. Now it's doing some height measurements. And now it's back to STIG calibration, which it does a second time. So lots of calibrations. It takes about 5 minutes to calibrate the beam. And that varies. Some spots are easier to calibrate than others. And the 128 nanoamp beam, which we're using at the moment, is one of the harder ones for it to calibrate. It's right at the edge of its working window. In a minute it will be calibrating the main field, and then you will see better what the calibration looks like. I can talk about the main field calibration when it happens. It's quite important. So here it is, main field calibration. You see that spots into the corner of the beam. Okay. So you can see the spots going to the corners of the oscilloscope. And what it's doing is it's moving the stage by, say, half a field in X and Y. So you've got a 1 millimeter field. It will move the stage by 500 microns, and then find the marker by deflecting the beam. And that's why the beam appears to be in the corner of the field, as you can see here. And that way it can calibrate the size of the field against the distances moved by the stage. The stage movement is monitored by a laser interferometer and is accurate to a few nanometers. And so this process enables you to calibrate the size of your main field to within a few nanometers. And this is what gives you good stitching. So all these calibrations are important. So that gives you it's doing the video adjust. So it's scanning the beam across your video adjust sample. And now it's taking photographs of the video adjust region and the cross, which you always get in your job. And the next thing, it will start looking for the 4 markers, and you can see it doing marker searches. And it looks like it's finding them reasonably happily. So it does a coarse search where you see the big cross on the screen, and then does the fine search, and now it's writing the pattern. So you can see where it's moving the main field to when it writes the pattern. You can't see the details, but this is the basic shape of the pattern which you're seeing here. And that's it, a very quick job, finished. So almost all calibrations, hardly any writing at all, which is not the most efficient way to run the machine. Ideally you'd have a job which lasts for considerably longer than the calibrations. So since calibrations take 5 to 10 minutes, you'd like the writing to take half an hour or so to be more time efficient. That isn't always possible. So this particular sample was very small for very good reasons, and that was all the writing that's required. So after the job's been written, the next stage is to unload the job and return it to the user. And that essentially is the same process as loading it, but in reverse. So we'd take the holder out, we'd vent the load lock, we'd take the holder out of the load lock, put it onto the bench, we'd take the sample out, put it into the user's sample box, and then place the sample box back into the trays which the users use, but of course this time it goes into the finished box rather than the box of samples to be run. And then you can come and collect your sample, develop it, and so forth.
So once the E-beam has written the job, you just you log into the website, log into E-beam lift and view completed, and then you need to look up the job, which is GIG0614, and then you have some pictures. This is a registration job, so it takes some photos of the markers, but the key information of what actually happened in the job is contained in the log file. There's 3 log files, but the short log file and log long, and then EMA log, which is really for Stephen Tom's benefit. So if you look at the log file, there's an abundance of information here, which too much to go into at the moment, but it gives you a lot of information like the substrate tilt, which on my sample was not great. That's quite a big tilt. It also gives you information such as this is when it's trying to find the marker, so this is the backscatter electron signal as it scans across the marker. So again, this is not a great marker, but that's because it's aluminium and silicon. And then it's got the actual positions of the markers, but these are all things for registration.
Okay, so we saw when we were loading this sample that there were some problems with the tiltedness of the sample, and this was really caused by the fact that the sample was very small and mounted onto a silicon piece. But very often we can have problems which are self-inflicted by the user, and it's worth spending a few minutes just thinking about top things which cause problems and ways to avoid them. So let's go back right to the beginning. If you remember the sample box and the labels on it, it's quite hard to label the sample box because the top surface is rough. But it's very important to write neatly on there because the operator needs to be able to identify your sample correctly with the list on the website. You'll also notice that the user writes some numbers on the back of the sample box to identify where it goes when the samples are loaded. You should make sure that your sample box is clean, both front and back, before you start writing on it. So when it's submitted, it's nice and clean. Otherwise, confusion can easily happen. If there's previous numbers written on the back of the sample or on the front of the sample, it becomes very hard for the operator. Secondly, when you're preparing your sample, make sure that it's clean underneath. Any resist at the back of the sample means it doesn't sit flat, and the operator has to spend more time trying to get it flat or may send it back to you for you to clean up yourself. Thirdly, the diagram telling the operator which way round to load the sample is very important. The diagram we saw in this situation was very clear. It said there was a cross at the bottom left corner. The cross was very easy to see. It was a joy to load. Sometimes people have diagrams that are very hard to follow. You've got to imagine that the operator has never seen your sample before. They've only got a few minutes to load your job because they've got lots of other jobs to load. The diagram needs to be clear and show straight away which way round the sample goes. Another thing to think about is clamping. A lot of people don't like too much of their samples clamped, but if your sample isn't clamped properly, securely, it doesn't lie flat, and then we can't run it at all. So please make sure that there are 2 or 3 millimeters free for the clamp to sit. Otherwise, it becomes very difficult to load.